This is the supplementary video for Lecture 21, and we shall finish all the leftover problems in exercise 16. Okay, let's start with number 22. This is actually a geometric problem. So we need to find the point on the curve y equals to root of x that is closest to the point 3, 0. So to understand the situation, let's draw a rough graph. So first, the curve of y equals to root of x. So this one should be familiar. So it has got a horizontal tangent at the number 0 and passing through 0, 0. And moreover, the graph looks like this. So this is the graph of y equals to root of x. So we are looking for the point on the curve that is closest to the point 3, 0 on the x-axis. This means if this is the distance given by this point and this is the distance given by this point, we see that all these distances are different. And we want to find a point with the smallest possible distance to the point 3, 0 over here. So that's basically what we want. Okay, so how should we proceed with this problem? So let's first recall the distance formula. So if I have got 2 points, x1 and y1, and x2 and y2, so then their distance between these 2 points is simply going to be the square root of x1 minus x2 squared plus y1 minus y2 squared. So this is actually the distance formula between these 2 points. And also recall another fact, that minimizing d is the same as minimizing. So essentially, this follows from the point that first d is greater or equals to 0, and second, over the interval 0 to infinity, so the function y equals to d squared. So this is actually going to be an increasing function. So let's actually say that if this is the smallest possible value d can take, then this will be the smallest possible value d squared can take. So by saying that this is the smallest possible value d can take, this means all the possible d is sitting to the right. And then if that's the case, then all the possible value of d squared will be above this point. And this fact holds vice versa. So if this is the smallest possible d squared can take, then this will be the smallest possible d can take. So this is how to see the minimization of d squared is the same as the minimization of d. Now let's start working on this problem. So let xy be a point on the curve. So this will tell me that the y coordinate is precisely root of x. Okay, so in order not to cause any notational conflicts, let me just set z as the square of the distance from xy to 3, 0. So then this way, I know that z is going to be x minus 3 squared plus y minus 0 squared. But knowing that y equals root of x, so I have x minus 3 squared plus root of x squared. So simplifying and expanding everything, so I get x squared minus 6x plus x, that would be minus 5x, and then finally plus 9. So that will be my function z over here. And we wish to minimize this function, this z, well, with the restriction that x sitting in 0 to infinity, because my point xy can be anywhere on this curve. And the smallest possible x coordinate we can get, it will be the 0, namely the left end point of this curve. And largest x coordinate, well, the x coordinate can be as large as you want. So that's how I get my domain over here. All right, so this is the function we wish to minimize, and the domain looks like this, and the rest will simply be a standard procedure. So dz over dx, so this is going to be 2x minus 5, and this guy equals to 0, means x equals to 5 over 2. And the corresponding z value will be z equals to 5 over 2 squared minus 5 times 5 over 2 and plus 9. Okay, so the first one will be 25 over 4, and the second guy will be 25 over 2, and the last guy will be 9. So the first two guys will simplify as 25 over 4 with negative sign, and for the 9 over here, we will just rewrite it as 36 divided by 4. And what we will get is 11 over 4. So that will be the function value at x equals to 5 over 2. Okay, so we also need to compare the function value at the number 0 and at the limit at the infinity. All right, so let's actually do that. So if x equals to 0, so this will imply that z equals to 0 minus 5 times 0 plus 9, and the answer will be 9. And as x approaches positive infinity, so what I will get is the following. So z, I will just rewrite z, it will be x times x minus 5 plus 9. So this will be x will be very large, x minus 5 will be very large, so the product will approach positive infinity, and a very large number plus 9 will still be very large. So that's how I see that this guy approaches infinity. All right, so 11 over 4 is smaller than 3, and then it's certainly much smaller than 9, and this will be certainly much smaller than infinity. This way, we see that the function z equals to z of x has no absolute max, and then z of 5 over 2 equals to 11 over 4. So this is the absolute mean. Okay, so this is what you can do using the modified closed interval method. Alternatively, you could also use the following argument. So if dz over dx, so if this is actually equals to 2x minus 5. So this guy will be greater than 0 if x is greater than 5 over 2, and then less than 0 if x is less than 5 over 2. So then this way we see that the domain 0 to infinity is separated into two parts, 5 over 2 and 0 to 5 over 2 and 5 over 2 to infinity. So then you see that the function is going to be decreasing for the first and increasing for the next. So this way you could also see that this at the 5 over 2, we get absolute minimum. So either way, we can see that the function takes absolute minimum when x equals to 5 over 2. Okay, but to formulate the answer, let's see what we want. We want to find the point on the curve. We are not asked to find the distance. So that's why you need to actually figure out the y coordinate over here. Okay, so if x equals to 5 over 2, then we see that y is going to be equals to root of 5 over 2, and this guy can be rewritten as root 10 over 2. So with this y coordinate, we can formulate our answer so that the point that on the curve that is closest to the point 3, 0 is 5 over 2 root 10 over 2. Okay, so that will be the answer to this problem. All right, so over here, I would like to give a remark regarding the second fact. So suppose we didn't know that minimizing d is the same as minimizing d squared, and we will set z not as the square, but simply the distance by itself. Then, well, what we have to deal with will be z equals to square root of x minus 3 squared plus 1 minus 0 squared. And after simplification, what I will get will be the square root of x squared minus 5x plus 9. So starting from here, if you compute dz over dx, what you will get is simply going to be 1 over 2 root of the whole thing by the chain rule, and then times 2x minus 5 over here. So if you start your analysis over here, so then you set dz over dx equals to 0, so you will still get x equals to 5 over 2. So this solution of the critical number you will get from here is the same. But also, if you want to set the denominator equals to 0, so if x squared minus 5x plus 9 equals to 0, you actually find that there is no solution for this guy. So at the end of the day, you will also get only one critical number, namely x equals to 2/5. And then you compute the z value over here, and you will find that the z is simply going to be square root of 11/4 or root of 11/2. And the rest of the procedure is basically all the same. So as x approaches 0, z approaches root of 9. As x equals to 0, z equals to root of 9, and x approaches infinity, z is also approaching positive infinity. So you see that the solution will be completely the same, but the only difference is you have to deal with this extra denominator, and also you need to argue that this derivative is defined everywhere, so there's no extra critical numbers. So I hope from this you will be convinced that minimizing d is the same as minimizing d squared. And also, as you could see from the comparison, so using this fact, the procedure is much more simplified. You do not need to worry about this factor in the denominator at all. Okay, so this concludes my discussion to number 22. Now let me continue with number 23. So we need to find the points on the ellipse 4x squared plus y squared equals to 4 that are farthest away from the point 1, 0. Okay, so just recall a little bit about the knowledge of an ellipse. So the standard form for that ellipse will be x squared divided by a squared plus y squared divided by b squared equals to 1. So here we can set a, b to be greater than 0. We call this formula to be the standard formula because if you draw the diagram, or if you draw the curve on the xy coordinate, you will find that your ellipse will be passing through positive a and minus a on the x-axis, and positive b and minus b on the y-axis. Yeah, that's actually so this is why this formula is the standard formula for the ellipse because of this. Now for the ellipse in the problem statement, so in order to make this form, we need to divide everything by 4 so that the right-hand side becomes 1. And if you divide everything by 4, what you will get is x squared plus y squared divided by 4, and 4 is precisely 2 squared, and this is going to be equals to 1. So the graph of this ellipse looks like the following. So let me just draw the coordinate axis, then let me actually draw an ellipse. And then the ellipse looks like this. And moreover, let me move it around. So the x-intercepts will be minus 1 and 1, and the y-intercept will be minus 2 and 2. So yeah, this is how it looks like in this problem. All right, so we are looking for a point on this curve such that this is actually the farthest away from the point 1, 0. So we are looking for a point on the ellipse that has the maximal distance to the point 1, 0. So that's basically what the problem is asking about. Now let's proceed as follows. So let xy be a point on the ellipse. Also, let z be the square of the distance from xy to 1, 0. So remember, in the previous problem, we said that minimizing the square of the distance is the same as minimizing the distance. So for this problem, we will just use the same principle. So minimizing the distance is the same as minimizing the square of the distance. So then from the distance formula, I see that my z is going to be equals to x minus 1 squared plus y minus 0 squared. So this will simply be x minus 1 squared plus y squared. All right, so from this relation over here, you could actually solve y squared out of the equation. So this will imply that 4x squared plus y squared equals to 4. So this will tell me that y squared is going to be equals to 4 minus 4x squared. Okay, so we can plug in the y squared over here. So as to conclude, my z is going to be x minus 1 squared plus 4 minus 4x squared. So this will be a function depending on only one variable, x over here. And we can further simplify the function. So all you need to do is to multiply x minus 1 squared out so as to get x squared minus 2x plus 1. And then together with the minus 4 minus x squared, you could get minus 3x squared minus 2x plus 5. All right, so that will be the square of the distance in terms of x. And we are going to maximize this function. But notice that the domain over here, so the domain of x will be from minus 1 to 1 because the curve is sitting on the ellipse. And the smallest possible x coordinate will be minus 1, and the largest possible x coordinate will be positive 1. All right, so that concludes the part of mathematicalizing the problem. Okay, so now let's proceed to get the derivative of z. So dz over dx, so this is quite easy. So that will be minus 6x minus 2. And if we set this guy equals to 0, what we will get is x equals to minus 1/3. Okay, so then this is the only critical number we have. And now let's actually compute the function value. So if x equals to minus 1/3, then z is going to be equals to minus 3 times minus 1/3 squared minus 2 times minus 1/3 plus 5. Okay, so simplifying, I will get minus 1 over 3 and then plus 2 over 3 and then plus 5. And the answer will be 5 plus 3 over 1 over 3. So the answer will be 16 over 3. All right, so that will be the square of the distance when x equals to minus 1/3. And we also need to know the z values when x equals to minus 1, but this is pretty easy. So if x equals to minus 1, z equals to minus 3 times minus 1 squared, minus 2 times minus 1, and then plus 5. And the answer will be minus 3 plus 7, which will be 4. And if x equals to positive 1, so then I will get the z equals to minus 3 minus 2 plus 5, and the answer will be 0. All right, so we need to compare which one is larger, and obviously, well, 16 over 3, so this is going to be larger than 5, so it will be larger than 4. So this guy will be the absolute maximum. So the conclusion is z takes the absolute maximum at x equals to minus 1/3. So z takes absolute max when x equals to minus 1/3. All right, so this is actually the conclusion by the calculus. Now to formulate the answer, remember we need to find the point. So which means we need to get the y coordinate as well from this formula. So then all you need to do is to plug in x equals to minus 1/3 over here, and that way you will be able to solve the y coordinate. So y equals to plus or minus square root of 4 minus 4x squared, and 4x squared will be 1 over 9. So yeah, this is actually going to simplify as 2 times square root of 8 over 9, and the answer will be plus minus 4 root 2 divided by 3. All right, so this will be the y coordinate. So now we are ready to answer the question. So the point that farthest away from 1, 0, so minus 1/3, positive 4 root 2 over 3, and minus 1/3, negative 4 root 2 over 3. All right, so that will conclude the discussion to number 23. Okay, number 41 is an interesting but tricky geometric problem. So it says the following. So a cone-shaped drinking cup is made from a circular piece of paper. And how do we make that? So we can cut out a sector. So this is actually the sector that's missed from the circular paper. And then we join the edges of CA and CB. So basically we attach these two sides, and that way we will be able to get a cone-shaped drinking cup. So in this form over here. Okay, so the question is to find the maximal capacity of such a cup. All right, so to understand the situation, let's first draw a picture. So let's say this is the resulted cone-shaped cup we obtained by attaching CA and CB. So then we need to actually figure out the dimensions, the important dimensions of the cone. So namely, we need to know the height, and we also need to know the radius of the base. All right, so how do we obtain this information? So first thing we should note is the following. So first, this AC over here will be the same as this length over here. So now we assume that the original paper was circular with radius capital R. So that's how we see that the hypotenuse of the triangle formulated by lower h, lower r, and this is actually going to be of length capital R. All right, so this will give us the first relation between these two variables. Let me actually write down the definition of first. So let lower r be the radius of the base of the cone. Let h be the height. So then from the geometry, we see that capital R squared equals to lower r squared plus lower h squared. So this simply follows from the Pythagorean theorem applied to this right triangle. All right, so now let's look at what we want. We want to find the maximum capacity of such a cup. So then so this means we need to maximize the volume. So let's see what the volume is. So let V be the volume of the cone. So you should know from your high school geometry then V equals to 1/3 pi r squared h. So that's the formula for the volume of a cone. Then you should know from your high school geometry that V equals to 1/3 pi r squared h. So this is the formula for the volume of a cone. And now notice that the lower r and lower h are related by this equation, and moreover, the capital R over here is now regarded as a constant. So that way we can get rid of the r squared from this relation. So because this will tell me that lower r squared is going to be equals to capital R squared minus lower h squared. So we will simply replace my r squared over here by this guy. So that way we express the volume as a single variable function, namely pi times capital R squared minus lower h squared times h. So it will be a single variable function depending on the height. Okay, let's figure out the range of h. So first, my h has to be strictly greater than 0. And well, indeed, you could say that h can take 0. So when h equals to 0, what you get is simply this circular paper regarded as a cone with 0 height. So, but we certainly do not want this case. So the largest possible value of h, well, you can see from this picture that it cannot be larger than r. So because in this picture, you see that the adjacent of this angle is supposed to be strictly smaller than the hypotenuse of this angle over here. So, but then, so that means h has to be strictly less than r. Well, you could also consider what happens when h equals to r. So if h equals to r, that means the radius is actually going to be 0. And the radius equals to 0, that means this circumference equals to 0. So this circumference should be the same as the arc length of AB over here. So this arc length being 0 simply means, well, the sector you cut off is simply going to be the whole the whole circular paper. So basically, yeah, if this is actually what happens when your h is very close to r. So yeah, then if you cut out this big sector, what remains will simply be this small part over here. So this is what happens when h is close to r. All right, so this will be the range of my h. All right, so this finishes the step of mathematicalizing the problem. And now let's look at the derivative. dv over dh. So well, using this so let me actually do the derivative by multiplying everything out. So that will be r squared h minus h cubed prime. And the derivative of this guy will be 1/3 pi times r squared minus 3h squared. Okay, so this is my derivative. And you see that this guy exists everywhere. So you do not need to worry about the critical number where it does not exist. And moreover, dv over dh equals to 0. So this means r squared equals to 3h squared. So that h will be the square root of 1/3 r squared. So you can rewrite this guy as r divided by root 3. All right, so that will be the critical number for h. And let's look at the function value at this critical number. So if h equals to r over root 3, so this will tell me that v is going to be equals to 1/3 pi times r squared minus 1/3 r squared times r over root 3. And you do the arithmetic by yourself. At the end of the day, what you will obtain will be 9 root 3 at the bottom. And on top, I should have got 2r cubed. Okay, so this is actually going to be the volume we obtain at the critical number. Okay, to see whether or not we get the absolute max or absolute min, let's look at the limit of the function at the endpoint. So as h approaches 0, so my v is going to be equals to 1/3 pi times r squared minus v is approaching 1/3 pi times r squared minus 0 squared times 0. So this is going to give me 0. So if h approaches r, so similarly, we'll see that v is approaching 1/3 pi times r squared minus r squared times r. And what you will get is still going to be 0. So comparing these three values, you'll find that this function value at the critical number is actually the largest. So that's how we see that v takes absolute max when h equals to r over 3. Okay, let's see what we are asked. We are asked to find the maximal capacity of such a cup, and we have obtained that the maximal capacity is going to this guy, so that way we can formulate our answer. So the answer is the maximal capacity of the cup is 2r cubed divided by 9 root 3, and that will finish this problem. We are left with two problems, namely number 42 and number 54. Allow me to be lazy by reusing the supplementary video I filmed last semester for these two problems.